Last time we have seen how to obtain the solution of a non-homogeneous linear differential equation of nth order, and we have seen the general method. Now here we want to see some short methods, means we want to see how to obtain the general solution of a given non-homogeneous differential equation if our q of x is a particular types of functions, and this method is very effective method. The method which we discussed in the previous article is the general method. Now to find the particular integral corresponding to the q of x of the non-homogeneous differential equation f of dy is equal to q of x, there are some short but effective methods to find the particular integral corresponding to some particular types of functions q of x, and we want to see these types of functions. For these type of functions we want to find, or we see the some short method to find the particular integral. We know how to find the complementary function. Now here if q of x is e to the power ax, second if q of x is x to the power m, where m is a positive integer, if q of x is of the type sin ax or cos ax, fourth, if q of x is of the type e to the power ax into v, where v is any function of x, and the fifth, if q of x is equal to x into v, where v is any function of x. Such type of q of x want to see the short methods. If our q of x is not of this type, out of these five types, if q of x is not of this type, then we have to use our general method. Just we have seen in the previous example, in that q of x is sec to x. In the last lecture example, we have seen the q of x is sec to x. In that case, we are unable to use any method from these five methods. Such type of q of x, then we use the general method. Now we see first for the q of x is equal to e to the power x. Now remember that throughout in this course, we consider this f of d is equal to d to the power n plus a1 d to the power n minus 1 plus dash 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 a n minus 1 d plus a n. This is a polynomial in d with constant coefficient. We consider our in our discussion throughout f of d is to be this for this topic. Now consider the differential equation f of dy is equal to q of x, where q of x is equal to e to the power ax, means a differential equation of the type f of d of y is equal to e to the power ax. How to find its particular integral? For that purpose, we want to see the two theorems. Now the theorem 1, if f of a is not equal to 0, if f of a not equal to 0, then 1 upon f of d operate on e to the power ax is equal to e to the power ax upon f of a. If we operate 1 upon f of d on e to the power ax, it comes to be e to the power ax upon f of a, provided f of a is not equal to 0. If f of a is not equal to 0, then we can write in this way. Now we want to give the proof of this. See here, f of d is what? D to the power n plus a1 d to the power n minus 1 plus dash 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 plus a n minus 1 d plus a n. Now from this we first write f of a, and f of a means in this result we substitute d by a. We want to use this later on this equation 1. F of a is equal to a to the power n plus a1 into a to the power n minus 1 plus a2 into a to the power n minus 2 plus dash 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 plus a n minus 1 into a plus a n. We call this as to be 1. Now, here we know that e to the power x is equal to e to the power x. We take the derivative of e to the power x. Derivative of e to the power ax is equal to a e to the power ax b square e to the power x is equal to a square. Now, derivative of e to the power x, we know that the derivative of e to the power x is a into e to the power x. The second derivative of e to the power x means the derivative of a e to the power x, a is outside, and the derivative of e to the power x is again a into e to the power x. Therefore, it becomes a square e to the power x. Similarly, if we see third derivative of e to the power ax, means d cube of e to the power ax is equal to a cube into e to the power ax, and go on continuing in this way. N minus one third derivative of e to the power ax is equal to a to the power n minus 1 into e to the power ax, and the nth derivative of e to the power ax is equal to a to the power n into e to the power ax. Then we multiply the above results by an minus 1 that is a1 into 1 respectively, and add, means here we multiply this by an, this by a n minus 1, this by a n minus 2, and so on, this by a1, and this by 1. And then we add all this, we get this e to the power n, e to the power ax plus a1, d to the power n minus 1, e to the power ax plus dash 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 a n minus 1 d e to the power ax plus a n e to the power ax. If you do not understand in this way, then you start from f of b operate on e to the power ax. F of b operate on e to the power ax. This is equal to, write in the bracket, what is f of b? Write in the bracket f of b as to be d to the power n plus a1 d to the power n minus 1, a2 d to the power n minus 2 plus dash 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 a n minus 1 d plus a n bracket complete, operate on e to the power ax. And then if we simplify the bracket, then we obtain this term after simplifying this. But we know that we have just seen the nth derivative of e to the power ax is a to the power n e to the power ax. Now n minus one-th derivative of e to the power ax is a to the power n minus 1 e to the power ax, and so on. A n minus 1 derivative of e to the power ax is a e to the power ax, this term as it is. And now we take e to the power ax common from the right side, and for the left hand side we get in the square bracket d to the power n plus a1 dn minus 1 plus dash 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 plus an minus 1 d plus an square bracket complete, operate this on e to the power ax, means we take this as to be common from this e to the power ax from the right side. The same way here we take e to the power ax common from the right side, means in the bracket we get a to the power n plus a1 a to the power n minus 1 plus dash 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 plus a n minus 1 into a plus a n bracket complete e to the power ax. And then we substitute the value of this bracket as to be f of d, and this bracket is f of a. Means we obtain this result f of d operate on e to the power ax is equal to f of a into e to the power ax. Now we operate 1 upon f of d on both the sides of this. We obtain this 1 upon f of d operate on f of d e to the power ax is equal to 1 upon f of d operate on f of a e to the power ax. But by the definition, we know that 1 upon f of d operate down f of d e to the power ax is equal to e to the power ax. We have seen this result, and f of a is to be constant. Therefore, we take it outside of the operator, means we get e to the power ax is equal to f of a 1 upon f of d operate down e to the power ax. And we know that since f of a is not equal to 0, it is given in the statement of the theorem. Therefore, we divide this equation by f of a. Then we get 1 upon f of d operate on e to the power ax is equal to e to the power ax upon f of a. And this completes the proof of this theorem. We want to use this result to solve the examples to find the particular integral of non-homogeneous differential equation if q of x is of the type e to the power ax. Now here we want to see in the next result if f of a is to be 0. If f of a is to be 0, then we know that d minus a is a factor of f of d. If f of a is 0, then we know that by factorization theorem, d minus a is a factor of f of d. Now suppose this factor d minus a repeated r times. Suppose this d minus a, this factor repeated r times, then we are able to write f of d as to be in the bracket d minus a bracket complete to the power r into phi of d, where phi of a is not equal to 0. Means we write f of d as what? In the bracket d minus a bracket complete to the power r into phi of d, where phi of a is not equal to 0. This means this d minus a factor repeated r times, right? And then we want to see if it repeated r times, then if we operate 1 upon d minus a to the power r into phi of d on e to the power ax, then it comes to be x to the power r e to the power ax upon r factorial into phi of a. And this is the statement of the next theorem. See, this is the statement of the theorem. If f of d is equal to d minus a to the power r into phi of d, where phi of a is not equal to 0 and r is a positive integer, means r is a natural number, then 1 upon f of d operate on e to the power ax, this is equal to 1 upon d minus a to the power r into phi of d operate on e to the power ax. This is equal to x to the power r e to the power ax upon r factorial into phi of a, where r is a natural number. Now to give the proof of this theorem, for that purpose, we use the principle of mathematical induction. And I have told you so many times that this principle of mathematical induction is very important theorem. By using this theorem in mathematics, we want to give the proof of so many theorems. And this is one of them. Now, for to give the proof by principle of mathematical induction, what we want to prove or what we want to show for that purpose, we call that statement as to be the PR statement. You may use any notation, PR, PK, PM, whatever it may be. We use their notation PR since the statement is given in terms of the R. Now, let PR be the statement that 1 upon f of d operate on e to the power ax means 1 upon d minus a to the power r into phi of d operate on e to the power ax is equal to x to the power r e to the power x upon r factorial into phi of a, where phi of a is not equal to 0 and here r is the natural number. Now we assume this is the statement PR. Now, what is the technique? By using the principle of mathematical induction to give the proof, we use the step 1. Means in this step, we want to check that in this PR statement, if we choose R is equal to 1, then this statement is true or not. This is our step 1. Choose R is equal to 1. If we choose R is equal to 1, then 1 upon f of t operate on e to the power ax is equal to 1 upon d minus a into phi of t to the power r. R is 1. Therefore, we write only d minus a into phi of t operate on e to the power ax. Now we operate 1 by 1 operator, inverse operator, 1 upon d minus a. First, we operate 1 upon phi of d on e to the power ax. And for that purpose, we use the previous theorem. We have seen that if f of a is not equal to 0, then 1 upon f of d operate on e to the power ax is equal to e to the power ax upon f of a. I will repeat this previous theorem statement again. If f of a is not equal to 0, then 1 upon f of d operate on e to the power ax is equal to e to the power ax upon f of a. Using that theorem, if we compare this bracket, square bracket, with that previous theorem, then here it is given that phi of a is not equal to 0. Therefore, if we operate 1 upon phi of t on e to the power ax, this must be equal to e to the power ax upon phi of a. Since phi of a is not equal to 0, we get this as to be 1 upon phi of a e to the power x. Result of this. Now we take 1 upon phi of a is constant. Outside of this inverse differential operator, we take 1 upon phi of a is outside and we operate 1 upon d minus a e to the power ax. We know the formula for this. We operate this 1 upon phi of a as it is. If we operate on this, we get e to the power ax integration of e to the power minus ax into e to the power ax dx. Right? We have seen this result. Now this becomes e to the power 0 is 1 and integration of dx is x. Then we obtain this term x e to the power ax upon phi of a. Or if we rearrange this, we write this x has to be x to the power 1 e to the power ax upon 1 factorial into phi of a. Means in that result, in the PR statement, if we choose r is equal to 1, then that statement is true. In that statement, we consider only the left hand side and we obtain the right hand side after doing these calculations, not directly. right? And therefore, what we can conclude, the P1 statement is true. This is the step one by the principle of mathematical induction. Now we consider in this step two, we assume that Pk means in the statement, if we choose R is equal to K, then statement is true. Or you may choose R is equal to M, then the statement is true. Means in step 2, you may assume either Pk is true or Pm is true. The notation is dummy. You may choose K, M, L as you like. For our simplicity, we choose here Pk. We assume that Pk is true. Means in the previous result, instead of R, if we choose K, then this statement is true. This is our assumption. And with the help of this assumption, we want to prove that Pk plus 1 is also true. If this is true, then by the principle of mathematical induction, we are able to conclude that this statement is PR is true for all natural number R. Right? Here we assume Pk is true, and from this want to check whether Pk plus 1 is true or not. If it is not true, then our result is not true, or the statement in the theorem is not true. If this Pk plus 1 is true, then the given statement is true for all natural number. Now here, this is our assumption. Pk is true means what? In that PR statement, if we choose R as to be K, then this is true. Means 1 upon D minus A to the power K into phi of t operate on e to the power ax is equal to x to the power k e to the power ax upon k factorial into phi of a. This is our assumption. Now with the help of, we want to show that this result is true for k plus 1 or not. Means we consider the left hand side as to be 1 upon d minus a to the power k plus 1 into phi of d operate on e to the power ax. Then we split this d minus a to the power k plus 1 as to be d minus a into d minus a to the power k. By the rule of power, we write this in this form, and then we first operate 1 upon d minus a to the power k into phi of d on e to the power ax. But by our assumption, this is to be 1 upon phi of a into k factorial x to the power k e to the power ax. We use this result directly here. We have assumed this. This is equal to how much? X to the power k e to the power ax upon k factorial into phi of a. Therefore, we obtain this left hand side as it is, this is equal to 1 upon t minus a, and this is x to the power k e to the power ax upon k factorial into phi of a by our assumption 1, or we call it as to be 1 by using that. Now again here 1 upon phi of a is constant, k factorial is constant. You take outside of this operator, then we get 1 upon phi of a into k factorial, then operate 1 upon d minus a on x to the power k e to the power ax. And then we operate this, or directly we operate this. Now here, if we operate this, we know how to operate this. This is e to the power ax, integration of e to the power minus ax, and this q of x as it is. Now we take, this is constant, 1 upon phi of a into k factorial. We are able to take outside of the integral sign, and this e to the power minus ax, e to the power ax is e to the power 0x, means e to the power 0 is 1. Means we obtain what? If we simplify this, This is equal to e to the power ax divided by phi of a into k factorial into integration of x to the power k into dx. We obtain this. And we know that what is the integration of x to the power k? This is x to the power k plus 1 upon k plus 1, provided k is not equal to minus 1. You remember this. This integral is x to the power k plus 1 upon k plus 1, provided k is not equal to minus 1. Now we rearrange these two terms. Below two terms, we write this as to be k plus 1 into k factorial. And we know that n factorial can be written as n into n minus 1 factorial. Using that result, we write this k plus 1 into k factorial as to be k plus 1 factorial and the remaining term as it is, and we get this x to the power k plus 1 e to the power ax divided by k plus 1 factorial into phi of a. Means we obtain the right hand side. Means in the statement of PR, if we substitute R by K plus 1, then this is also true. And to prove this thing, we have assumed that this PK is true. We have used this concept here. And therefore, finally, we can say that this pk plus 1 is also true. And therefore, we can conclude that by step 1, step 2, and by principle of mathematical induction, this PR is true for all natural numbers. And this complete the proof of this theorem. Means what we have proved, if f of d is equal to d minus a to the power r into phi of d, where phi of a is not equal to 0, then 1 upon f of d operate on e to the power ax. This is equal to 1 upon d minus a to the power r into phi of d operate down e to the power ax. This is equal to x to the power r e to the power ax upon r factorial into phi of a. And we want to use both these theorems to solve the examples. In the theorem 1, we have seen that if f of a is not equal to 0, then 1 upon f of d operate on e to the power ax is equal to e to the power ax upon f of a. We have seen this thing. Now we stop our today's lecture.